Smart Culture, Mathematics.
The derivation of the present value annuity formula can be understood using the formula of a geometric series. So let's break it down step by step. Suppose you're receiving or paying an annuity of R per period for n periods, and the interest rate per period is equal to I. The present value of the first payment received or made 1 period from now is R. The present value of the second payment, in other words 2 periods from now, will be R over 1 plus I. The present value of the third payment, 3 periods from now, will be R over 1 plus I squared, and so on. The present value of the nth payment will be R over 1 plus I to the power of n minus 1. Now, what we'll do now is we'll sum the present values. So if you add up all these present values, you get R plus R over 1 plus I plus R over 1 plus I squared, and so it goes on. So here you can see, here we have a geometric series with the first term R and the common ratio 1 over 1 plus I. Now we can rewrite this common ratio as 1 plus I to the power of negative 1. So the sum S of a geometric series with n terms, a first term of A and a common ratio R, is given by the following formula. And this formula is applicable when R is smaller or less than 1. Now, let's relate the geometric series formula to the present value annuity formula. Now remember, A is equal to R. We've determined that previously. And this can also be equal to X times 1 plus I to the negative 1. In the context of the present value annuity formula, if we're looking at the first payment of the annuity, which is 1 period away, its present value would be R. However, if R is the result of discounting a future payment X by 1 period at an interest rate I, then R can also be rewritten as X multiplied by 1 plus I to the negative 1. So 1 plus I to the negative 1 represents the present value factor for a single period at rate I. To relate this to the present value annuity, if you're thinking of the annuity as a series of future payments X that you're discounting to their values 1 period prior to when they occur, then the first of those payments would be X multiplied by 1 plus I to the negative 1. So in a present value annuity context where you want to express the first payment as a discounted value of some future payment X, then R can also be written as X multiplied by 1 plus I to the negative 1. So now that we have the value for A, which is X multiplied by 1 plus I to the negative 1, and we have the value for R, small letter r, which represents the common ratio, that is 1 plus I to the negative 1. Now that we have these values, we can substitute these values in the geometric series formula. So instead of writing A, we write X multiplied by 1 plus I to the negative 1. And instead of writing R, we write 1 plus I to the negative 1. So now you'll see we have P is equal to X multiplied by 1 plus I to the negative 1. And this is being multiplied by 1 minus 1 plus I to the negative 1 raised to the power of n, and all of this is divided by 1 minus 1 plus I to the negative 1. Now the 1 plus I to the negative 1 and the numerator next to the variable x is moved down to the denominator, so we get rid of the -1 exponent. So now we have x multiplied by 1 minus 1 plus I to the -n divided by 1 plus I multiplied by 1 minus 1 plus I to the -1. So what happens now? The denominator can be simplified to 1 plus I minus 1. Now 1 minus 1 is equal to 0. So the denominator becomes I. So that means the present value of a series of payments is equal to x multiplied by 1 minus 1 plus I raised to the -n divided by I.
And that's a wrap on today's fascinating journey through the world of knowledge. Don't forget to hit that subscribe button and join our ever-growing community of curious minds. We can't wait to embark on new educational adventures together.